Hi everyone. So today this is an example of heat integration problem. As you can see, this one the objective of the problem is to do the following, which are hot and cold composite curve, problem table algorithm, and grand composite curve. So before that, we must start with the end in mind. So I would like to show you the end product of this problem. So on data T mean 10 degrees C, as you can see, the top one will indicate you the hot utility required. It is the length between the most left of the table of the graph until the next point of the top one. It indicates you the hot utility, and the most bottom one from the left side until the point will indicate you the minimum cooling utility required. So as you can see, there is no heating required here, and minimum cooling utility required only 100 kilowatt for data T mean 10 degrees C. For 20 degrees Celsius data T, there is a slight heat required at the top. As you can see, the length between the most left of the graph to the next point, which is 20 kilowatt, while the most bottom one at the left side until the point which touches the graph, which is 120 kilowatt for cooling utility. So to make it a clear difference, for data T mean 30 degrees Celsius, as you can see, the top one will require 80 kilowatt of hot utility, while cold utility, as you can see, 180 kilowatt. By comparison, this is data T mean for 40 degrees C. As you can see, hot utility required only 140, and cold utility required at the most bottom one, which is 240 kilowatt. To get the hot and cold composite curve, we must first draw a table of stream, temperature supply, temperature target, MCP, and Q. So the product is something like this, and we have identified 3 hot streams and 3 cold streams. So you must just tabulate accordingly. From the table just now, we can combine the 3 heat streams into one line, as shown, and the 3 cold streams into one line. As you can see, this is for data T mean 10 degrees C. So that is the point where the pinch happened, which is the data T minimum. As for this problem, there is no heating utility required above the pinch, as the hot and cold streams are in line with each other, and at the below pinch, the minimum cooling utility required is 100 kilowatt. As you can see, there is a gap between the hot, the most left, until the first point of the cold utility. So that is the minimum cooling utility for this problem. So for the hot and cold composite curve, there is a law that can be applied here, as the cold stream combination can be shifted to the left or the right, depending on the data T mean that is required. So for this special case, we do not need to adjust anything, because data T mean obey 10 degrees Celsius. For the step 2, we have to draw the graph of composite curve based on increase of the temperature. So for the problem table algorithm, there are 2 main equations that need to be known, which is TH. For the new TH, temperature hot will minus with data T mean divided by 2, while TC new will be TC plus data T mean divided by 2. So this is the steps taken. For 3 hot streams, there are the Tmin that is chosen is 10. So each of the temperature will be minus by 5. So the cold temperature will add up by 5, and this is the new adjusted temperature. The amount of heat required will remain the same as the delta T is the same. After getting the adjusted temperature, first you must arrange the temperature accordingly from the lowest to the highest, and then you have to plot the streams from the supply temperature to the target temperature. For the 3 hot streams, as you can see, the cooling of the hot streams, and the cold streams, the heating of the cold stream occur. And for this one, the main highlight is to identify for each interval of the temperature, which is each row, for Cp hot minus Cp cold. So for this table, as you can see, the Cp hot dominating, and from the additional of the Cp hot we get 11, and the amount of heat required is to multiply the delta Cp net and the delta T interval. So as you can see, you can get the energy required. And for the next interval, you can see there is a demand of the cooling from the light side. So the Cp hot will be minus with the Cp cold, and we will be getting 2. And the amount of energy required is around 20. Do this for each of the interval, and as you can see, the Q, the amount of energy, there is no negative energy that is in the table, and therefore we can proceed with the cascade. Since there is no negative of heat, so we will assume there is no cascade. No cascade will be required for this problem, and we can straight away plot the grand composite curve. To draw the grand composite curve, first you must plot the y-axis, which is temperature, and the x-axis, which is the enthalpy. And from the table we get here, from the from the interval 345 to 305, so 345 will be plotted with x at 0. Here, 345 and x at 0, and then the next at temperature 305, it will be plotted with the 440 somewhere here, and the graph will be continue like that with the accumulation of Q from each of the interval. So from this problem, as you can see, from different delta Tmin, as it increases, we can conclude that the total utility will also be increased. As you can see here, there is no hot utility and there's 100 kilowatt of cold utility. And then the delta Tmin 20 degree, we see the accumulation of total utility required is 140 kilowatt. The next one is delta Tmin 30 degree. The hot utility and the cold utility will sum up to 260 kilowatt. And the last one is delta T 40 degree C will have total utility of 380 kilowatt. So we can conclude that as the delta T increases, the total utility also increases.